Why are fertilizer plants so dangerous? And if they are so dangerous, why are they so heavily relied upon by the agricultural industry? Well, it all has to do with food. All plants need nitrogen. Plants use nitrogen to make proteins and nucleic acids. That's DNA. There's a ton of nitrogen in the air that we breathe, but it's not the kind of nitrogen that plants can use. And there aren't enough organic or natural sources of nitrogen to make enough food for Earth's growing population. That's why fertilizers are so important. Fertilizers are responsible for sustaining the food supply for 1/3 of Earth's population. That's crazy. We would likely starve without fertilizers. Now, all nitrogen-based fertilizers are made with ammonia. It is a covalently bonded compound with 1 nitrogen atom and 3 hydrogen atoms. 500 million tons of ammonia are made each year using a method called the Haber process. Every year, humans consume roughly 25 million tons of nitrogen, mostly as proteins. As the world's population rises, our demand for nitrogen will rise with it, as will our dependence on the Haber process. The Haber process and fertilizer production is so dangerous because of the high temperatures and pressures required to make ammonia. You might remember learning about theoretical yield, actual yield, and percent yield in chemistry class. Well, these terms are extremely important when it comes to making ammonia using the Haber process. So let's look at those definitions. The theoretical yield is the calculated or expected amount of product that can be made in a perfect world. The actual yield is how much product is really made. This result is never greater than the theoretical yield. In reality, chemists never obtain as much product as theoretically possible. This can happen for a number of reasons. Maybe not all reactants are completely converted into product. Sometimes reactants can undergo side reactions, or sometimes it is difficult to separate the desired product from a mixture. Basically, a lot of reactions are inefficient. Chemists like to measure how efficient reactions are because they're all about keeping track of matter. The good news is there are steps that chemists can take to tweak reactions. This is really important when it comes to the Haber process. Let's look at what actually happens in the Haber process. So nitrogen is combined with hydrogen to make ammonia. Let's look at how percent yield is applied in a real-world example. When 100.0 grams of nitrogen combines with hydrogen and forms 20.0 grams of ammonia, what is the percent yield? To solve this problem, we will need to find the theoretical yield first. Start with the reactant mass and calculate how much product should be created in a perfect world. The formula mass for N2 is used to convert from grams of nitrogen to moles of nitrogen. That gives us 3.57 moles. So how much ammonia should this amount make? Look at the balanced chemical equation. For each mole of nitrogen that reacts, 2 moles of ammonia are made. The molar ratio is 2 to 1. Then use the formula mass for ammonia to convert to grams. If this reaction were to go perfectly, then 121.59 grams of ammonia should come out. Alright, so we've got our theoretical yield. The problem tells us that we actually made 20 grams of ammonia. Not too much. So how efficient was this reaction? Chemists use something called percent yield to do this calculation. Percent yield is a comparison of what you actually got from the experiment and what you should have gotten. To find the percent yield, you divide the actual yield by the theoretical yield and multiply by 100. Don't worry, you do not have to memorize this formula. It is on your STAR reference materials. So here's the percent yield for our example. Yikes, that is a terrible yield. But the good news is, chemists know how to tweak reactions. The unreacted started materials can be recycled back into the reaction over and over and over again, helping the Haber process achieve a 98% yield. So in actuality, the Haber process is extremely efficient. But even modern chemistry has its limits. How far will we push the technology to keep feeding the world's growing population? Well, that's for you future chemists to figure out. Think you can come up with a safer process than the Haber process? There just may be a Nobel Prize waiting for you. All right, I'm out of here. See you later.